For those who don't know or haven't heard of Wood, we were formerly AMEC Foster Wheeler, formerly AMEC, and formerly MacTech. And I just tell you that because you'll see slides along the way that have those logos in them. We're all the same company, and we still work as some of those companies in different places. We're still MacTech in some places in New York. So I was asked to give a presentation on groundwater sampling, and I was given a variety of topics to cover. So I broke these down into two basic categories: groundwater sampling, what you need to think about when you're developing a groundwater sampling plan, and what you need to think about for data interpretation. So wide variety of things that I will be going over a little bit more in depth. And then I have 3 case studies at the end, which hopefully will bring a lot of these concepts into some reality with some sites that actually we've investigated. So data quality objectives. Before you can do anything, you really need to establish what your data quality objectives are. And with groundwater, it changes for every type of investigation scenario that you'll be going through on any site. So these are the base data quality objectives that I could think of for groundwater, starting with the presence, absence, and eventually getting to hopefully remediation and evaluating long-term effects. So what is your data going to be used for? In a presence absence characterization or site inspection, you're really looking, is the contaminant there or isn't it? Is this really a site or isn't it? So as you look at these sites, you may be the first people on the site. You may never have been investigated before. And that's good in some ways because you get to install the wells where you want them. You don't have to, consider existing wells and what they might mean to your investigation. But then you generally have limited subsurface information that you might also get with previous investigations. So again, with previously investigated sites, you're going to have some understanding of the subsurface. You'll know where groundwater is generally if there are wells already on site. But with those wells, you're going to have to start evaluating what they mean. Are they in the location, and how do they affect what you're going to be looking for? When you're designing your sampling plan, you're really looking at biased locations. Where's the most likely place that the contaminants would be? And you're going to put in longer well screens to hit a wider range, and hopefully, because you don't know much already, get the biggest area that might be contaminated. So the results might have less meaning as you go along. So after that, if you figure out you do have a site, you're really looking at the nature and extent. That's either a remedial investigation would be the full blown, or you're just looking at the vertical and horizontal distribution. How far is it traveled? As you're thinking about this, you want to think about where your contaminants of concern are. Where are they going to be located in the aquifer? How far might they go? What are the chemical and physical properties that might have some bearing on where those contaminants are in the aquifer? And you're going to be looking at that in relation to the subsurface conditions. You're going to start looking at what's your geology. Do you have clays? Do you have aquatides? Do you, is this sand and it's going to go straight down to the bedrock? So those types of investigations might be entirely different wells than you're looking at for a site, just a site characterization. Your sample program design is going to get to more discrete sampling. You're going to be focusing in on fractures if you're in bedrock, or geologic units that are more transmissive. And you're probably going to be looking for multi-level sampling. Vertically, where is it? Impacts to receptors. So as you're trying to decide if you have impacts to receptors and you're thinking about the potential and you're evaluating the wells you might have on site already, are your monitoring wells representative of drinking water wells in the area? Are they in the same aquifer? Are they at the same depth? Are you hitting the same fractures? One of the things you can do to figure that out is the easiest thing would be go do residential sampling. If they are contaminated and the same contaminants may be coming from your site, but you're still going to have to do probably a little more work to figure out the actual connection. This is where you probably, if you can, look at borehole geophysics. start looking in those wells. It requires a lot more work. You have to pull a residential pump. It's not always something that's going to be available. But once you start looking at what those bedrock conditions are, assuming bedrock, you're going to start be able to figure out whether fractures are connected back to your site. You can do packer sampling on those, put in inflatable packers and sample discrete zones once you know where fractures might be. And that's just evidence that'll lead you back to your site. And if you can't get on into a residential well, you can always do this nearby, but you may or may not have much information on that residential well before you do that. And another thing you probably want to think about, all right, which way are we going? Is the effects of residential pumping on your site. You can put transducers in the residential wells fairly easily most of the time, and wells on your site, and see what pumping effects might have on the site where you have contamination, to give you a better understanding of where that be. And you'll see in one of my case studies a little bit later some of the effects that residential pumping can have. Another receptor from groundwater would be surface water discharge. This is another place where you might be looking for multi-level points. Do you have groundwater gradients, nested wells, wells near each other, evaluating the differences in those to figure out if you have discharges to the surface water. And of course, surface water could not only be a drinking water source, but could also be ecological receptors in there as well. And pore water might be a good way to evaluate whether you might have a receptor in that sediment. So a pore water sample is a groundwater surface water interface sample. It's generally putting something into the sediments and figuring out if you have contamination in that. And generally that's an evaluation of the benthic organisms, which are part of the food cycle. Once you figured out your nature and extent, you're really starting to look at remedial options, and your types of wells that you might be looking at this point change again. Where is your contamination? You're not looking at receptors and who's impacted. You're really trying to figure out where you want to focus. Excuse me, your remedial efforts. If you're pumping and treating, are you pumping and treating on the right fractures? If you're injecting, are you injecting into the right unit that has the most contamination? And the nature and extent, you'll know where it is, but you may have well screens that are too long if you're using other wells that are already installed to try and figure this out. So if you have a 20-foot well screen that's spanning several types of geology, and you have a couple of transmissive units in there, it doesn't really tell you where that is. And if you start treating over that 20 feet, it may be less effective than if you figured out, oh, it's the top one, which is down 10 feet. And if you can focus on that, your remedial option, your remedial treatment will be much more effective. At this point, you're probably going to start looking at geochemistry. If you start pumping and treating what might be in the water that causes additional problems, fouling, if you're sparging, what kind of chemical reactions are going to happen that you may not know if you don't have that information. So it can have an impact on how effective your remediation is. So at this stage, your wells again might change, and you have to start looking at what it is you want and will it meet the objective for what you're doing. And then the last one I had was remedial effectiveness and long-term monitoring. After you're done with your remediation, how are you going to evaluate whether it's being effective? Trends, are you expecting trends to go down? So you need to make sure, again, these wells are located in a position that can give you this information. Again, you may or may not be able to use wells you've already installed during the investigation. Again, it may mean going back out and putting in more wells to figure that out. Monitoring wells. How do you select a monitoring well location? Some things to think about again. What is your data quality objective? That's the first thing every time you go to do something you really need to think about. And then you really have to start building that conceptual site model. Where are your receptors? What are you looking for? What kind of geology might impact the contaminants that you have? How is it going to act in the environment? And this is, you probably start looking at some, if you're doing bedrock, looking at some in situ evaluations with borehole geophysics or high resolution profiling to figure out the distribution of contaminants in your aquifer that you're evaluating. And then something to think about, I've got some slides on what to think about if you have existing monitoring wells and how you can use them and how they may be limited. So when you're looking at borehole geophysics, what you're looking at is the structure of the bedrock. Do you have fractures that might be important and transmissive? Do you have interconnection between wells? You can start figuring that out when you start doing the borehole geophysics. So you're doing several evaluations in the borehole. At the other side, you have a series of pictures that came from a site in New York. You're seeing caliper, bedrock structure, and then optical televiewer on the other side. So this is giving you a picture of where the more transmissive zones are. So you can see that they start lining up. I guess this doesn't work. Oh, so I think you can see the picture right there is that we're in a pretty good area for transmissivity for water, and that might be a good place to install a well. And if you do this on bedrock, you're more likely to get it right. You know, you're just guessing if you just go in blind and drill a hole and stick in a screen, unless you have some other information that might help you understand. Groundwater profiler, it's good for VOCs. You're looking at membrane interface probe, laser-induced fluorescence, things we talked about earlier today. And then this is a place where you can start taking discrete groundwater samples. You get them within a foot. So as you're going through this high resolution and doing everything else, there are options in there to take samples as you're going down without taking your tooling out and going back down and taking discrete samples. And again, you'll see an example with this in it in one of my case studies. And this, again, allows you to more accurately place monitoring wells. A limitation on this is it gets expensive, and really it comes down to the size of the site and what the implications of not knowing this is going to get you. When you're installing new monitoring wells, again, you think about those data quality objectives. I think sometimes people forget that they change, and how you install that well and the purpose of it might change what kind of well you need. You got to be looking at the contaminants of concern. Are they light? Are they petroleum? They're going to be at the top of the water screen. Are they dense products, coal tar, PCE, and they're going to sink? They're dense, non-aqueous, and they're going to be at the bottom of the water column. And then the depth of water. You've got to make sure you put in a well that's sized for a pump that you can use. If your water is greater than 22 feet, peristaltic pump isn't going to work probably well, and so you're going to need a 2-inch well or special pumps. There are ways to do it. It's just not the most convenient way. So if you have a way to, if you're thinking about this beforehand, a 2-inch well for something deeper is easier. Types of monitoring wells: standard wells, PVC with slotted screen. In those screens generally are put in 10-foot sections, but you can modify those to whatever section you need. People just generally put them in at 10-foot. And as you're refining your investigation, you're going to want to think about what size screen meets the needs that you have. Hybrid wells, a well that would span both the overburden and bedrock. And there are some situations where that is your most transmissive zone. The material right over the bedrock and the weathered bedrock might be acting as one unit entirely. So that might be something you want to consider, that they're not two distinct aquifers at that point. They're really acting in the same. If you leave an open hole, there are issues. Contaminants can migrate more easily. You don't know where the sample you have is coming from if you don't have the fractures defined. But there are reasons that people leave them. You can put in passive diffusion samplers, things like that to start understanding more of the bedrock structure and where the contaminants are. But it's always, I think, better to put a well in if you have that option. And I think people leave these open sometimes for thinking about what they're going to do in remediation as extraction wells or maybe injection wells. And then multi-level monitoring wells. Not only can you do nested wells, but there are several systems out there that are single casing systems that will give you some information as well. Get the continuous multi-channel tubing, which I've used on a couple of sites, West Bay, Waterloo, Flute, and then multiple nested wells and barcade wells. So I'm not going to get into a lot of detail on that, but here is one example. This is the CMT well, the continuous multi-channel tubing. And you can see on the far slide, you have 7 openings in that well. It's a one long tube. You can see in the middle that we've decided that's our screen length. What you end up doing is cutting holes for the screen on the channel. We opened up 2 of them so that, as you can see in that last slide, you can have water level in one, tubing in the other, and you can do your low flow sampling quite easily. You cut the holes, you wrap the screen, you decide on your screen length, you're plugging up the ends to make sure you're not getting anything, and you build your well. And you can do multiple channels. The way we have it set up, we'd end up with 3 and just water level in the middle. If you have existing monitoring wells, you really need to start thinking about some things before you use it. Again, why was it installed? Is it in the right location to meet your needs? Do you know how it was constructed? So just because it's in the right location, if you don't know how it was constructed, where that well screen is, it may not meet your needs. If it's really in the right location and it's a well that would cost a lot of money to reinstall, it's a deep bedrock well, you might consider some simple borehole camera optical teleview to give you that information. But you need to make a decision on how important that well is, and the cost to do this is to install a new one. And when you're thinking about these, when was it last sampled? Oftentimes they need to be redeveloped before you just go out and grab a sample if you really want to make it useful to your investigation. Groundwater sampling techniques. So I think this is one we're all familiar with, low flow sampling. This is the EPA Region 1 latest and greatest SOP. In the slide, you can see standard setup. You have a water level meter, peristaltic pump, looks like a YSI field parameter meter, which has dissolved oxygen, conductivity, oxidation reduction potential, pH. Missing anything? I think it has turbidity, but turbidity is probably not best done within the flow cell. You should have a separate meter. You can see in the next picture, in a couple of slides, you'll see a picture of a bypass that I think is the preferred way to set up to do that turbidity reading. Low flow is great because it's applicable for most contaminants of concern. It can be used with almost any pump. But as you're thinking about these pumps, some of them are better than others and they each have their own pros and cons. I think that the Grundfos pump ends up heating up a lot when you're going very deep. So if you're doing VOC sampling, it might not be the best pump for the job that you have to do. So in low flow sampling, and you can see in the picture there, set up with a bypass for the turbidity sampling. So you collect the turbidity sample before it goes into the flow cell. And that's I think the correct way to do the turbidity readings. So why are you collecting these field parameters? I think that I think people in the field who are collecting samples lose track of why they're doing that sometimes. the primary reason we're doing it is to indicate that the well is at equilibrium with the formation. So once you're getting steady readings on all the parameters, plus or minus whatever percentages, can't remember them off the top of my head for each of them. Once you get those steady readings, that indicates that you're getting formation water in theory. So the water coming in is representative of the water in the aquifer. But you may also want to be using those field parameters for other reasons in your evaluation. And I think this is where the field staff need to understand these things when you send them out, or your field staff when you guys go out and collect them. The first one just means that you are getting constant readings. They don't have to be accurate. They just need to be the same. So you can meet that objective without having accuracy. Once you decide you're going to use these results for something else, you're really looking at having those meters calibrated correctly, make sure they're reading right, and that level of data is going to meet the needs you need. So some of the reasons that you might want to use these parameters in your evaluation, high or low pH could result in other contaminants forming. You could change chromium to hexavalent chromium. You can do geochemistry can do weird things on you. So understanding this might help you identify why you have certain conditions on your site. Conductivity or oxidation reduction potential may be used to evaluate if you have a chemical plume. Not only hazardous chemicals that you might be evaluating, but if you're down gradient of a landfill, you're looking at potassium, calcium, sodium. Those things can also be indicative of where your plume is going, that you have a problem starting and that your hazardous contaminants might be not far behind. And dissolved oxygen can give you some information on discharge or recharge areas. So as you get closer to a water body, is that DO showing that you're in a discharge or a recharge area. So as you're in the field, if you're seeing things that don't make sense, you have to start questioning them then. So field staff should be saying, hey, I'm seeing pH of 11. Is this typically what I've seen? Does that make sense? Or is my meter not working? So there's just a bunch of things that these field parameters are used for beyond just are you at equilibrium and is this a representative sample? So make sure you explain those data quality objectives before you collect the data. No purge sampling. This assumes water within the well screen is at equilibrium. It's most appropriate for long-term monitoring. So you really want to have some information before you install or take a no purge sampling, which I'll get into them a little bit in the next couple of slides, a couple of examples of that. But what you really need to think about is you want to know what are your flow rates, what are some of those field parameters, what kind of concentrations are you seeing them in the top or the bottom of the well. And that's why long-term monitoring, it's great. You can put them in after one sampling event and come back at the next one, whatever interval that is, and pull them out. These methods are very low investigation-derived waste that you have to deal with on the other side. You're generally not, collecting parameters, so you don't have to bring the well to equilibrium by pumping and collecting a lot of parameters, so it takes less time. During early investigations, there may be reasons that you use these. If you have a well with a long screen and you want to see if there are contaminant gradients, you might want to put in some of these samplers, which I'll get into here. Hydrosleeve. Hydrosleeve is an open bag with a reed valve at the top. You put them in there closed, and they sit there until you collect the sample. So I've had them installed at one of my sites. I do it on a 15-month basis. So after the end of one sampling event, put these in, come back, and pull them. These open as you pull them out, so you really have one shot at setting them, unless you pull them out really slowly so that they don't open. But as you pull them out, the water pressure opens the valve. Once it's full, the valve closes and you've got your sample. So where it sits within the well screen is where that water sample is collected. This first slide, the weight is at the bottom. So it's sitting in the well fully stretched out. You're going to get the 2-foot sample above that. If your well screen isn't long enough for collecting that kind of sample, so you're less than 2 feet into the water, the second slide shows a top-weighted hydro sleeve so that it sits further in, probably up at the bottom, and as you pull it out, it fills, and so you get a greater distance. And then you just poke a hole in it and collect your sample. I have this installed at one of my sites that is a long-term monitoring site because it has a very fine particulate, and anytime you pump it, it just gets stirred up and floats, and it won't settle out again. So we set these after each one has 15 months out, and there's less disturbance as we pull them out. And this is a site that I need to collect for metals. So this is appropriate for, again, all sample types because, it doesn't require, passive diffusion, which is the next one. And these also come in HDPE, so you can use them for PFAS. Passive diffusion bags, I think probably everyone knows about these. These are closed bags that are filled up with deionized water. They're generally LDPE. VOC contaminants can pass through by diffusion. It's sitting within the well screen. You leave it for a certain period of time, and over that time it equilibrates with the aquifer, and you get your results. It's good for VOCs except for MTBE, MIBK, and styrene. There are probably a few others. And you can stack them in the well, again, to get those gradients. If you have a 20-foot well, you can put one at the top to see, are your contaminants shallow, and one at the bottom to see if you have that gradient. Another type of no purge sampling would be a grab sample. And there's several instances where you can get these in a well or from the subsurface. So packer sampling, as you can see, there's a packer in that slide. Put those in, you're doing other things, measuring other parameters. You can have a grab sample at that time. You're not equilibrating with the aquifer. You're not taking the time to parameters within the acceptable a sample, and that sample tells you something. It may not be representative of the aquifer, but for deciding whether that's a contaminated zone compared to others within your well, that might be a good way to do it. And then we have sample point samplers. You're collecting your soil samples, the screen's there, they pull back and the screen's exposed, and you can collect a groundwater sample as you're doing that. Again, it's not equilibrated. You're not making sure that your parameters are all stabilized. But if you're evaluating a large area and as you're going, you just want some general information about where contamination is, where it isn't, or set a well, okay, at the end, we're at the extent, let's set it 10 feet beyond here as a monitoring point. It gives you some information. Again, you got to think about your data quality objectives. Who hasn't gone out in the field and seen a hole full of what? You start digging, stuff comes in, and you want a sample of that. It may be perfectly acceptable to collect that sample. It tells you something. It may not be the same as a well. Floating oil, you're gonna be looking for petroleum. You might want to know if there's PCBs in there, but metals may not be a good sample to take out of this. There are all sorts of things you come along, pits in buildings where machinery sat that are full of water. You want to sample. You just need to think, what are you going to use that data for, and how does it fit in your conceptual site model, and what would it might lead you to do in the future if you're using that to evaluate potential future actions that might be perfectly acceptable. So, quick review on sampling drinking water. So residential drinking water, you really want to understand some of the things about the plumbing, especially depending on what your contaminants of concern are. If your site's a metal site, you probably want to understand the age of the house, what kind of piping they have. Could they've used lead solder? If you're sampling for PFAS, how much Teflon is in there? How could that affect your sample? Is there any treatment systems, sediment, water softeners, or carbon? And really, what is your objective of collecting this sample? Are you collecting the sample to evaluate the risk to the receptor? Or are you trying to tie this back into groundwater contaminants that might be at this extent from your site? So if you're trying to evaluate the risk to receptor, I think the appropriate place to do that might be at the kitchen sink. If you're trying to evaluate what groundwater conditions are as close to the ground as you can, you're going to take that sample as far close to the well as you can. That's going to help you realize more what's going on in the aquifer than traveling through the piping system, which might have other things that are affecting. If you can get information on the well, you're going to be better off. How deep is it? Is it drilled? Is it dug? How old is it? Those things don't often exist, or property owners don't often have them. Data quality and interpretation. Data quality. Generally, what you're looking at are field blanks, equipment, material blanks, rinse blanks, and duplicates. Field blanks, you take an aliquot of DI water and you pour it out in the field into the bottles you're using. This is meant to represent any contaminants in the atmosphere in the proximity that might be affecting the samples you're collecting. The equipment blank is a blank that goes through the pump and the tubing, and you collect your sample from that prior to sampling. So what this is evaluating is does the equipment have anything in it that might have an impact on the sample results that you get. Differentiated from a rinse blank, which is a sample after you've collected your sample. So collect your samples. This is evaluating how well your decon procedures are working. So this would be on any equipment that's reused. Generally not the tubing. Tubing is usually dedicated to a well or disposed afterwards. So this is just was your equipment cleaned properly? And of course, this is going to have effect however many samples you collected with that. Any results that you get from a rinse blank is going to apply to those. So if you collect 10 samples and then do your blank, those 10 samples, whatever the results are from that, have that qualifiers with it from what those results are. If you do it every time, you'll know it's just to that one sample, but no one does that. That's a lot. And then duplicates in groundwater generally don't change. They're usually very close. If they do, it could tell you that there was a change in the system as you were collecting that sample. Did your pump rate change somehow? Did you all of a sudden get some DNAPL or LNAPL come into the sample as you were collecting? These are the things you usually see when those are different. And your data interpretation. It all comes down to the conceptual site model. You collect all this data and you put it into conceptual site model. If you're looking at the data and you put it into your conceptual site model and it just doesn't fit, these are things you need to question and reevaluate. Did you collect your samples right? Are they in the right location? You have to run through all of that again to make sure. And I have a great example of where they got all the way through remediation, set up a whole system, and the data didn't really fit what you should have thought was going on. And again, you have to take those QA/QC results you get every time you get a hit in one of your blank samples. You have to evaluate that back against the sample results that you've gotten on your well samples or your groundwater samples, and try to understand how that affects it. Just because it's there doesn't mean the sample has no value, but in some cases with really low detection limits, like for PFAS, a small amount might make your sample invalid and you need to resample. So be really careful on the lower the detection limit gets, the more important it is that you are careful on how you collect those samples and do your decon. Sampling methods also might have an effect on how you interpret your data. Turbidity, if you have a VOC sample with a couple inches of sediment in the vial, the lab is going to take that and dilute it. They're going to take aliquot of the water off the top, make a dilution and run it, because they're not going to put that sediment into their system. So that could bias your data low. If you get a sample result that's ND, you can't really be sure what that means. However, if you get a sample result that has a detect in it, then you're probably fine. It means it's really there and you've got a sample result. However, turbidity for metals has just the opposite. If you have turbidity in a metal sample, you're going to be biased high from the natural occurring metals in the sediment. As I mentioned before, pumps can have an effect on your sample results. We're using the right pumps. Did they heat up? And what might that mean to a VOC sample? Field parameters. Again, going back and making sure that those field parameters make sense with the data you have previously, with what you expected, and if it didn't, why didn't it? So, 3 case studies. 2 of these, the first 2 are bedrock sites, and the third one is an overburden. It's a private client site. It was a TCE site that they did injections and created a secondary problem with hexavalent chromium as a result of oxidation. The site had extensive groundwater sampling. They did the conceptual site model. They included geophysics and they put it into a 3D visualization, which I'll run here in a minute, to identify the most transmissive fractures, to really figure out where that contamination is and be able to focus the remediation where it needed to be. This allowed a focused in situ treatment, and they have met the cleanup criteria. So I included it because you don't see that very often. So this is a 3D model. We're seeing the aerial view. It'll flip up and you'll start to see the subsurface. You see wells, sampling points at the surface, and then fractures. A fracture trace study was done. You see the fracture subsurface expressed on the surface, and how they, they'll eventually get down to the most transmissive zone and show you where those sample, the highest sample concentrations were. So let's run this. Here we go. So the sample points are coming up now. And there are the bedrock wells, the fractures, see the heat pulse concentrations there. So going from the full to the most transmissive zone, and you can see as it flips up here, the groundwater results will start showing up. That was rock chip sampling, and this is the groundwater. You can see right on that fracture, the red, it'll turn again. So going through all of this allowed the technical team to really understand where that was, and they were able to do their injections right at the problem. And this, a couple more things. So these structures that are showing up now are trenches where they believe the contaminants were discharged. They line right up with the fracture and the highest concentration, so it fits the conceptual site model. I think that's it. So I think it's just a good example of, if you do it right, how you can really get to the end point that you're looking for. Oh, that's not what I meant. Okay. Oh, there we go. So the next one is the American Thermostat site in South Ciaro, New York. Background on this one is this was a thermostat manufacturer. They operated from the 50s until the early 80s. I wish this thing was working, but it doesn't seem to be. Down in the right-hand corner, that's the manufacturing facility. There's a black box outlining the area where they dispose the material on the ground surface. There are 2 wells up here on the the northwest that are supply wells to, I think you can see in the aerial photo, a mobile home park. And there are several wells along the boundary to the west as well, single residential wells. So the investigations began in the early 80s. This was an EPA Superfund site. They did extensive investigation and determined that the wells, all the way out to that extent, to the supply wells and the residential wells, were all contaminated, exceeding the groundwater criteria with the source down there. So this site, if you look at it, it's a 3,000-foot long plume. The question I have is, why is groundwater flowing that way? If you can see over on the western edge of the slide, that's a river, that's the Catskill River, and it's flowing south. So it really doesn't make much sense that this is doing this. So why is it doing it? It is doing it, but why? When we started a remedial system optimization in 2012 and turned off the pumping wells, shut down the system, and this is the conditions that really exist. It is under natural conditions flowing towards the Catskill River. So those wells that we have at the margins, the 2 supply wells for the mobile home park and the residential wells, all had that much of an effect on the system. But they had put in wells that span the entire length of the bedrock aquifer, over 200 feet deep, and they decided that the residential wells that they hooked the residents up to the water system, that those were open holes as well, so let's use those as extraction wells. So as they went through the decision-making process, they made all these decisions along the way and set up a whole remedial system, which they didn't really understand where the contamination was coming from. And because of that, they exacerbated the problem, and they set up a system that really didn't have any effect at all on the concentrations. So they ran it for 14 years and weren't seeing what they wanted to see. So they did an optimization. Again, this is another 3D model that I'll run through. We went in and we did passive diffusion bags, put those in these really long wells to see if we could find out if they were contaminant gradients. We did geophysics to find out where those fractures were, put it into this 3D model to model where those most transmissive zones were, matched it up with the PDB samples, Packer samples that we collected, and came to a better understanding of what was actually going on here. So again, you'll see this, lots of wells, you'll see the site and the Catskill River in 3D, the topography show up, and the wells as they come along. So I'll do my best to talk through it. Oh, that's not it. Oh, no. Let's try it again. There we go. So yeah, they had 16 extraction wells, overburden 16 bedrock. It's the site. You can see the wells, the 2 red points out at to the north. That's the monitoring system. The blue on the top are the soil samples where the source was. It's the top of bedrock. You see you have a little trough in the bedrock there. And that's the PC concentration in soil. So the bedrock groundwater potentiometric surface is there, showing up a little bit in the trough. So that's the concentrations in 2011. PDB samplers, you now can see in some of those wells the gradients indicating that it isn't ubiquitous throughout, which you wouldn't really expect. And there's the plume again. So the Packer sampling was done, and the bedrock fractures were added to the model, and they limited those to the fractures which produce water during Packer sampling. And you can see the colors. There's the aperture colors on the bottom over there. And we end up with, from this, are 2 significant transport zones heading right towards those wells. So now you have this understanding. Those wells were having a significant impact on drawing that water in the direction that it wouldn't naturally go. But also, that's where your contamination is focused. And this slide is a slide from the PCE plume in 2012. Same shape as you saw before. And after optimization, which limited wells back to the site, so we're only pumping close to the site now where the contamination is highest. You can see the effect it's had. The highest concentrations have pretty much bifurcated at the site. You have a small high level up at the north. Those 2 wells on the western side of the plume there, those are the wells that line up with the supply wells for the mobile home park. So those wells are now below standard, and the plume is getting smaller. So once you know what you're looking at, it is much easier to effectively treat the system, and it costs you a lot less money in the long run. So pumping and treating for 14 years accomplished nothing, but in a short period of time, I think they got the system up and running in 2015. You can do a lot more if you know where it is. Oh, and now CROUT, the Cold Regions Research Laboratory in Hanover, New Hampshire. And this is an overburden site. This site has 125 feet on average of unsaturated overburden and about 50 feet of saturated overburden. It's lacustrine overlying sand right on top of bedrock. So this is a TCE site with the initial investigations again in the 80s and 90s. These guys used a lot of TCE. They did experiments with TCE. TCE was part of their non-contact cooling system. They had a catastrophic tank rupture in the late 70s. It was a 10,000 gallon tank that lost 6,000 gallons of TCE all at once. So when our team went out to the site, they were expecting, this is a DNAPL site. We have high concentrations of TCE. They knew that from some of the previous investigations. This wasn't the first time out at the site. So they went out thinking, how do we, confirm or not confirm that DNAPL is or was present? So they went out with profiling to figure this out. They thought that was their best way of most cost effectively getting to that answer. So what they did end up showing was entirely different. Because of the profiling that they did, they figured that the conceptual site model is actually that they have a large soil vapor plume which is dissolving into the groundwater at that interface, and that DNAPL never really made it down that far. So you can see in the conceptual site model, the release is at the surface, and as it comes down, it's really just getting absorbed to the materials and doesn't make it all the way down to the aquifer as a DNAPL. But they do have a very large soil gas plume. This first graph is showing the log of the groundwater profile that they did. At the same time, they were collecting discrete samples. And on the monitoring well figure, the purple line represents the soil gas plume, which is about 5 million micrograms per cubic meter. They did the groundwater profiling, and the first set of numbers you see there, as they went through, they took a sample at the groundwater table. They were at 65,000 micrograms per liter. 5 feet later, that result was down to 310 micrograms per liter. And then by the time you get down to the bottom, which I believe is around 12 feet, down to 38 micrograms per liter. And this is particularly significant when you look at the second number over there. We have a monitoring well in there, and they took a sample from that 10-foot monitoring well screen. That result is 23,000 micrograms per liter. If you just had that result, you might interpret this data differently. You might look at that and say, well, that's a condition that represents potential DNAPL existing or previously having gotten there. So you'd be looking at a whole different way of remediating this. But by doing the profiler, they really could figure out that the interface with that plume was the issue. That's the source, not a DNAPL. And it's an entirely different way to think about the remedial options that you might have here. And so this is a picture. The two orange things are basically the major release locations, and you can see the groundwater concentrations coming out of each of those are very much lined up with the soil gas plumes from those source areas. I'm going to skip that one. Yeah. So this is the conclusion on it all. This is the same well that had the 23,000. You can see that on this axis. They started a soil vapor extraction pilot at the site, ran it for about a year, went out and took another sample from that well, and their sample results were down near non-detect. Now, to be fair, they thought they did it wrong. They put a passive diffusion bag in. They got these results back, and they said, there's no way that there was that much of an effect. They thought they hung the bag too high, and it wasn't in the water. So they went out and did it again. And indeed, that is the effect that the soil vapor extraction had on the groundwater. So that more evidence that is the source of the contamination here. And you can see over time, different places where the system is turned on and off, and you have peaks corresponding to that on the rebound. So in summary, really need to think about where your samples are coming from, that they're in the right locations, that you're meeting the objectives, and evaluate the data. If it doesn't make sense to your conceptual site model, you really need to figure out why. That's it. Any questions?
Questions about groundwater?
So we had a now retired QA person that would argue with our senior field engineer, saying that you couldn't use a parasolving pump for VOCs, that you have to use a bladder pump. I think it might even be documented. But anyway, I just was wondering what you guys have thoughts on that, because we did a bunch of field tests, and our now retired senior guy was convinced that after a period of time when the pump is flowing, that it's not a vacuum, it's a vacuum pump, and once it gets flowing and you're not flushing air, just like the groundwater, that it's more like a cost displacement pump. So I don't know if you guys have opinions on to have your field staff use a parasolving pump for VOC sampling if they're using the correct tuning.
Repeat the question.
So the question was, is it appropriate to use a peristaltic pump for VOC sampling? I think that is standardly what's done. If you have shallow water, that is how you collect the sample. I'm not sure that we've seen any evidence that they're any different between the bladder pumps or the peristaltic pumps.
Anybody else want to weigh in on that from your experience? Anyone?
I think there have been studies historically that show that the
volatilization during sample collection. But I think when you look at all the other minute ways in which we introduce the potential for volatilization during sample collection, that sometimes the practicality outweighs the many ways in which we are also affecting that sample before we get an analysis. So I think if you collected, 200 samples for the peristaltic and 200 samples for the bladder pump with the exact same body of water, you get vastly different readings because of the different ways in which we have opportunity to use variability of the samples. So one part of it is, I think the practice hasn't changed away from using peristaltics, even though perhaps the bladder pump is a better method to use.
Okay. Anyone else on that?
All right, so let's move on here.